Imagine you're maybe an engineering student, or perhaps you're just starting your career, and you're tasked with designing something for, let's say, a brand new train, like a really high-speed one. We'll call it the Velocity Express. How do you make sure that your design, and really every single bit on that train, doesn't just look good on paper, but actually performs, like flawlessly, safely, efficiently for decades? How do you balance, pushing the boundaries with cutting-edge stuff while making absolutely sure this train gets people where they need to go every single time, no problems? Today, we're doing a deep dive into the framework that tackles exactly those questions. RAMS in railway rolling stock engineering. And this isn't some abstract theory. It's a really meticulous, integrated way of doing things. It ensures everything from a tiny little bolt right up to the entire train works exactly like it's supposed to, consistently, safely, throughout its whole life. So, our mission today, we want to unpack what RAMS actually stands for.
Dig into why it became so vital in the railway world, and see how it's sort of woven into every single step of building and running a train. We'll look at the different roles it plays, the challenges it helps solve, and the kind of unique skills you need to actually make it all work. So yeah, let's get into this acronym, RAMS.
Okay, let's break it down. RAMS. It stands for four really critical pillars, fundamental to any kind of robust engineering system, really. Reliability, availability, maintainability, and safety. Each letter you see represents a really vital part of how a train performs, and honestly, its commercial viability too. So reliability, that's all about predictability, right? It's the probability that a system, or maybe just a component, will do what it's supposed to do without failing for a specific time or, a certain number of operations.
Okay. Like, how often does a train door not open when it should? Or close properly?
Exactly. Or think about the brakes not responding right. I mean, if you take a major city's metro system, even a tiny drop, like 0.1% less reliability across the fleet, that could mean hundreds of thousands of delayed commuters every single day.
Wow.
Yeah, and millions in lost revenue. It's not just inconvenient, it's got massive economic and operational consequences.
And that links straight into availability, doesn't it? Because a train could be super reliable in theory, but if it's always stuck in the depot being fixed,
it's useless, right? Exactly. Availability is the percentage of time a system is actually, operable, ready to go.
It's the difference between our Velocity Express sitting cold in the shed and actually speeding down the tracks, carrying passengers.
Precisely. High availability means more trains running, which means more revenue and, happier passengers at the end of the day.
Makes sense.
And that leads us straight to the next one, maintainability. This is all about how easy it is to keep a system running or how quickly you can fix it when something does go wrong.
Right. So if a critical part on our Velocity Express breaks, how fast can we swap it out or repair it?
Exactly. Good maintainability means less downtime, obviously, lower labor costs too, and often it simplifies things like managing spare parts.
And then there's the big one, arguably the most critical. Safety.
Absolutely. Safety. It's about the absence of unacceptable risk of harm to people, damage to property, or the environment.
So preventing the really catastrophic stuff like a derailment or total brake failure?
Yes, that's paramount. But it's also about minimizing risk at every level. Making sure a passenger doesn't trip getting off or preventing electrical fires, things like that. It's fundamentally about building trust and protecting lives.
Okay, so RAMS. But you mentioned the emphasis has shifted over time, particularly on availability and maintainability.
Oh, dramatically, especially in railways. If you look back, historically, many train operators were state-owned government operations.
Right, less competition.
Exactly, minimal competition. The main goal was often just providing network coverage, connecting places, getting a basic service running. The long-term costs, what we call lifecycle costs, or LCC, they weren't the main driver. Why? Because governments basically footed the bill, subsidized things.
So hang on. Before this liberalization thing, they weren't sweating the long-term costs nearly as much. How big a deal was that difference, really? Was it just inefficient?
It was a completely different world, a different ballgame, honestly. When liberalization happened, splitting the track management from the train operation, it suddenly created this competitive landscape.
Okay. Different companies bidding to run services on the same lines. And this wasn't just a small tweak. Suddenly, a manufacturer's entire bid for new trains could swing heavily on those long-term costs. We're talking like 30–40% of the bid evaluation sometimes.
Wow, that much?
Oh, yeah. Imagine buying something cheap up front, but it costs you an absolute fortune down the line. Liberalization basically forced the industry to face that reality head on.
And that really pushed RAMS, especially the A&M, right to the forefront.
That's a massive shift in thinking. But what about safety? Surely that was always the top priority.
Safety, yes, has always been paramount. Preventing accidents has been core since day one of railways. Initially, though, safety was often handled by just, well, sticking to established product standards,
Right.
making sure things were built to spec.
Okay.
But over the last few decades, partly driven by lessons learned from, well, some significant incidents, safety has become much more formalized, much more systematic.
Now it involves really robust processes, like defining specific criteria for what level of risk is acceptable. It goes way beyond just ticking boxes for technical standards. Proving safety isn't just a nice to have, it's mandatory. For the operators, for the authorities who give the final approval, that's called homologation, and even for the manufacturers themselves, because of product liability, it's about engineering minimal risk proactively, not just reacting.
Got it. So RAMS isn't just something tacked on at the end. It sounds like it's baked into the train's design right from the very start.
Exactly. Think of it like threads woven right into the fabric. It influences every single design choice, what materials you use, from the earliest, roughest sketches. In the railway industry, we often visualize this using something called the V model.
The V model.
Yeah, it's basically a diagram showing the system's life cycle. On one side of the V, you break down all the requirements, what the train needs to do. Then, as you move up the other side, you build, test, and verify everything against those initial requirements.
Okay, I think I can picture that.
And RAMS is integral. It's part of every single stage along that V.
Right, so let's follow our Velocity Express along this V model. Where does RAMS engineering first appear?
Right at the very, very beginning, in the concept phase. Before anyone's even cut metal or drawn up detailed blueprints, RAMS engineers are involved.
Really, that early?
Absolutely. They're comparing different design ideas, not just looking at the sticker price, but at the projected RAM and LCC, the long-term cost picture. They might pull data from similar projects, maybe older trains, to predict how different choices will play out over, say, 30 years.
So they're trying to balance the upfront cost with the long-term running costs.
That's the core goal right there, finding that sweet spot. The lowest purchase price isn't always the best value over the train's entire life. A design might seem cheap initially, but if it's going to need constant expensive maintenance, it's a false economy.
How does that help specifically with minimizing maintenance costs at this early stage? What are they looking at?
It's critical thinking. RAMS helps by pushing for design choices that cut down on maintenance frequency, how long tasks take, cost of parts. For example, they might argue for using a specific, maybe higher grade material for a really critical part.
Okay.
Or maybe they recommend a redundant system, a backup that kicks in if the main one fails. Or they might even suggest sticking with certain suppliers known for top-notch reliability. It's all aimed at stretching out those maintenance intervals and cutting down failures.
And safety in this concept phase.
Also crucial, they're doing early hazard analysis, identifying things that could potentially cause harm. That's a hazard. They define safety targets for key functions, these early safety decisions. They massively influence the whole system architecture, and that, as you can guess, directly impacts maintenance costs and even the final price tag of the train.
Okay, this is fascinating. So concepts are sketched out, influenced by RAMS. Then you move to nailing down the specifics in system definition and application conditions. What's the RAMS team doing then?
This is where the big ideas get translated into concrete specifications. You develop a detailed RAM plan and a safety plan.
What's in those?
They outline the whole RAMS organization for the project, the specific processes everyone will follow, the basic requirements for the train, and the methods they'll use for analysis. A really key task here is identifying all potential risks, not just technical or commercial ones, but specifically the risks of failing to meet the RAMS targets or risks related to product safety.
So more detailed hazard analysis.
Exactly. A preliminary hazard analysis identifies potential contributors to hazards. Then you define the specific safety requirements and functional requirements needed to control them, and you determine how good those controls need to be. For instance, setting a tolerable hazard rate, how often a specific hazardous event is allowed to happen, or defining a safety integrity level, or SIR.
SIL.
Yeah, safety integrity level. It's basically a measure of how robust, how reliable a safety function needs to be. Think of it as needing enough nines after the decimal point in its reliability figure to meet the safety goals.
Gotcha. Okay, so requirements are set. Now we're deep into the actual design work, system design and development. How's the RAMS engineer fitting in with the design team now?
They're right in the thick of it. Those high-level requirements get systematically broken down. For every subsystem, every single component, the RAMS engineer isn't just checking things off a list, they're an active participant in design reviews.
Doing what specifically?
They're constantly asking for and proposing the evidence needed to prove compliance. That could be anything: structural calculations, dynamic simulations showing how the train behaves, results from all sorts of tests. Component tests, function tests, system tests, full vehicle tests, environmental tests, even EMC tests for electromagnetic compatibility.
Wow, okay.
And making sure all the documentation is right, like fire certificates for materials or safety data sheets for fluids used on board.
So they're really getting into the weeds of the design. What kind of analysis methods are they using here?
They deploy some pretty powerful analytical tools. A common one is FMEC, failure mode, effects, and criticality analysis.
FMEC, sounds intense.
It kind of is. It's like a forensic investigation before anything actually breaks. You systematically look at every way a part could potentially fail, what might cause it, and what the effect would be. Does it cause a minor issue? A major one? A safety critical one? This helps make sure that one single failure doesn't lead to an unacceptable risk.
Right. No single points of failure if possible.
Exactly. And they also use things like fault tree analysis. That's more about looking top down from a potential hazard, like brakes fail, and figuring out all the combinations of component failures that could lead to it. This helps prove you can meet those tolerable hazard rates and check if your redundant systems are designed correctly.
And they're tracking all this.
Constantly. The RAMS engineer maintains a hazard log. It's basically a running list of every safety concern identified, tracking how it's being resolved, and collecting all the proof, all the verification evidence.
What if there's a conflict? Say a proposed design clashes with safety rules or the RAMS targets. Does the RAMS engineer have veto power?
Well, they immediately report it to the project team. If the designer responsible, maybe for cost reasons or timeline pressures, doesn't want to change the design.
Oh?
Yeah, then it gets escalated. It goes to an independent safety authority within the company. This internal body has the final say, making sure safety isn't compromised for other factors, the really important check and balance.
Okay, that makes sense. So moving from design to reality, manufacturing and installation. How do RAMS principles apply when things are actually being built?
This is where theory meets metal. The RAMS engineer works really closely with the technical publications team.
The people writing the manuals.
Exactly. Making sure the maintenance manuals and operating guides are crystal clear. Are the specified tasks, the intervals between them, the troubleshooting steps accurate, easy to understand? They also do something called an operating and support hazard analysis.
What's that look for?
It specifically identifies safety risks that could pop up during the actual maintenance and operation of the train, things technicians or drivers might face. That analysis can then lead to design changes, maybe adding safety guards or requiring specific safety procedures for staff or putting clear warnings in the manuals and training.
So it's about protecting the people who work on and run the train too.
Absolutely. And they'll often be on site during manufacturing and installation. To verify those maintainability assumptions we talked about, is it actually as easy to access that component as the drawing suggests? Are the estimated times to do a task realistic? They're also gathering quality assurance documents. And crucially, a system called FRICAS is set up early.
FRICAS, another acronym.
Yes. Failure Reporting and Corrective Action System. It's basically a formal process to track any failures or incidents that happen, even during assembly and initial testing. You analyze why it happened and implement fixes, whether that's a design tweak or a change in the manufacturing process. It's a vital feedback loop.
And that FRICAS loop keeps going even after the train leaves the factory.
Oh, yes. Once our Velocity Express is finished, tested, approved, and enters the operation and maintenance performance monitoring phase, FRICAS continues throughout its service life. You're constantly validating the train's actual RAM and safety performance in day-to-day operation. Are we meeting those safety targets? Are all the functions working as they should? And importantly, if any changes or modifications are made later on.
Like upgrades or repairs.
Exactly. They have to be rigorously analyzed to ensure they don't negatively impact safety or RAM's performance.
This sounds like where you really prove if all that earlier work paid off. How do you check if you met those RAM and lifecycle cost promises made to the operator? Are there consequences if you didn't?
Definitely. There are regular meetings with the operator specifically to analyze the field data. How reliable has it actually been? How available? Are the maintenance tasks taking the time we predicted?
And penalties.
Oh, absolutely. Contracts often include penalties if the agreed upon RAM or LCC targets aren't met. So There's a strong commercial incentive to get it right. But beyond just the contract, working closely with the maintenance teams in the depots is invaluable.
Why is that?
You get incredible practical knowledge about the product. It helps verify the theoretical predictions you made years ago during design. And all that feedback helps make the RAM and LCC calculations for the next bid much more accurate, reducing project risks down the line.
Right. That field data must be gold. It shows where the real weaknesses are, maybe unexpected wear on certain parts, brake pads, wheels, filters, or finding out it actually takes twice as long to swap out a component than planned.
Exactly. That's true continuous improvement. It feeds back into refining the design, making the next generation of trains more competitive, and avoiding costly redesigns.
Okay, let's broaden the view slightly. What about the supply chain? Does every little company making a bracket need a full RAMS team? And what about the relationship between RAMS engineers and the design engineers? You hinted there could be friction.
Great points. First, the supply chain. No, not every supplier needs the whole massive RAMS analysis package like the main train builder. That wouldn't be efficient.
So how does it work?
The requirements have to be tailored, broken down to match the specific thing they're supplying. You wouldn't ask someone making a simple mechanical door panel for a complex fault tree analysis. Instead, they provide specific inputs, maybe component failure rate data or recommended maintenance steps, which then feed into the manufacturer's higher-level RAMS work. They provide pieces of the puzzle. Now, about the dynamic with design engineers, yes, there's potential for natural tension there.
How so?
Well, think about priorities. Project managers and design teams are often focused on, the technical design itself, hitting delivery deadlines, keeping upfront costs down.
Makes sense.
But RAMS is focused on the long game. Service performance reliability, availability, lifecycle cost, and above all, minimizing safety risks. These different perspectives can clash.
Give me an example.
Okay, maybe a safety analysis shows you really need a redundant system for, say, the power supply, but that wasn't in the original plan. Adding it means more cost, maybe more weight, possibly delays, or perhaps a RAMS analysis dictates a certain maintenance interval for safety reasons, but the operator wants longer intervals to save money.
So the RAMS engineer can sometimes feel like, the process police are just adding extra hoops to jump through.
That perception can definitely exist. RAMS can sometimes be seen as just an extra burden, adding cost and time. So the RAMS engineer often has to be an educator, too.
I'm an educator.
Yeah. They need to explain why this analysis, this requirement, is necessary. Help the design team understand that, say, a safety analysis isn't meant as a criticism of their design. It's about systematically finding potential weak spots so you can mitigate the risks before they happen. Remember, it's usually about achieving acceptable risk, not some impossible standard of absolute zero risk. You do that by making failures less likely or by reducing the consequences if something does fail. I remember a case where a design team wanted to use a slightly cheaper power converter. Our RAMS analysis showed it would likely need 3 times the maintenance over its life and had a higher failure rate. In the long run, it would cost the operator way more. We had to lay out the LCC calculations, show the data, not just say no, to convince them the slightly pricier but more robust option was actually the better value.
That really underscores why starting that collaboration early is so important, right?
Yeah.
To avoid those clashes and redesigns later on.
Absolutely. When RAMS is built in from the start and everyone understands its purpose, it becomes a tool for optimizing the whole product, not just a compliance exercise.
So considering everything we've discussed, what makes a good RAMS engineer? It sounds like it's definitely not just crunching numbers in an office.
Far from it. A good RAMS engineer can't just be chained to a desk. They need to be out there visiting manufacturing sites, going to customer workshops and depots.
Why is that physical presence so important?
That's where you verify your assumptions. You talk to the technicians who actually do the maintenance. You see how things work in the real world. You gain that deep, practical product knowledge. Honestly, talking to the maintenance crews often reveals way more about accessibility issues or unexpected failure modes than any drawing ever could.
And technical knowledge. Do they need to be an expert on every single system on the train?
Not necessarily a deep specialist in every single domain, no. But they absolutely need solid fundamental technical knowledge of the product overall.
Enough to do what?
Enough to ask intelligent questions. To challenge the engineering team effectively when needed. To understand the implications of design choices. Without that base technical understanding, they're just collecting data. They can't really influence product optimization or safety effectively. I recall one RAMS engineer who spotted a potential issue in a new brake system design. Not because they were the world's leading brake expert, but because their grasp of the whole system allowed them to ask the crucial question about how it interacted with another system under specific conditions. That led to an important early fix.
And then, obviously, the core RANS expertise itself must be rock solid.
Oh, non-negotiable. Deep understanding of the relevant standards is key. Things like the EN 50126 series that basically lays out the whole RAMS process for railways, from concept right through to decommissioning, or EN 50129, which focuses specifically on safety-related electronic systems. Plus, they need mastery of the analysis methods we talked about, FMECA, fault tree analysis, and the software tools that go with them. And crucially, they need to be able to explain these often complex processes and why they matter clearly to both technical specialists and non-technical managers.
Okay, technical chops, standard knowledge. What about the softer side? It sounds like a lot of interaction, maybe even negotiation is involved.
Huge amounts. Soft skills are absolutely critical. They have to be excellent team players,
Yeah.
proactive, collaborative, able to talk to everyone from designers to factory workers to senior management to regulators.
And convincing people.
Communication and persuasion are paramount. They're often in challenging discussions daily. Negotiating with project teams about design changes, justifying costs to management, explaining risks to customers or safety authorities. They need to find agreements that work, but without compromising on essential requirements or, especially, safety. It's a balance, being open to hearing other arguments, but also having the conviction and the evidence to justify critical decisions, even when they might be unpopular initially. Building consensus around what's safe and smart in the long run, not just what's easiest or cheapest right now.
We've really covered a lot. It's clear that RAM's reliability, availability, maintainability, and safety isn't just some bureaucratic checklist. It's truly a fundamental, deeply integrated approach that shapes everything about how railway rolling stock is designed, built, and operated. It's all about optimizing how it performs, managing those long-term costs, and underpinning everything, ensuring safety throughout the train's entire life.
Absolutely. So maybe next time you're on a platform waiting for a train, or maybe you see one speeding past perhaps even our imaginary Velocity Express, take a second. Think beyond just the speed or the sleek look. Consider the incredibly complex layers of reliability, availability, maintainability, and safety that have been meticulously planned, analyzed, and engineered into its very being, all just to get you and thousands of others safely from A to B, day after day, year after year. And maybe think, from an engineering standpoint, about the constant, intricate trade-offs and vital decisions, all guided by that RAMS framework that had to happen behind the scenes to make that journey not just possible, but consistently reliable and secure for everyone on board. What might happen if even one of those letters was overlooked?